Hi friends, now we will discuss on the topic gasification of coal. This is the second part of this topic. In the first part we have discussed about the gasification process, its mechanism, then different types of reactors applicable for coal gasification and their comparison. Now we will see how the syngas produced after gasification can be made suitable for different types of downstream application. And the content of this class is syngas conditioning and cleanup, and then syngas utilization and IGCC and polygeneration options. As we have seen in the previous class that when syngas is produced in the gasifier, its temperature is very high and it contains number of impurities like say particulates, acid gases like SOx, carbon dioxide, H2S, etc. So, these need to be removed. And another fact is that for different type of downstream applications we need different type of syngas quality. So, as shown here in this table, if we see for power application, for hydroprocessing and for chemical applications of the syngas, we need different types of quality. Here sulfur, CO2 and CO concentration is provided for 3 different applications. So, we see here sulfur for power application requirement is 10 to 15 ppm weight basis, whereas for hydroprocessing it should be less than 1 ppm and for chemical less than 0.01 to 1 ppm. So, the degree of removal of sulfur compounds from the syngas is required in different extent. For carbon monoxide we see for power application there is no such requirement, but for hydroprocessing it should be less than 50 ppm on weight basis, and for chemical applications the carbon monoxide and hydrogen ratio should be maintained as per requirement. Different applications have different requirement of hydrogen is to CO ratio, but if we see the CO and H2 composition in the raw syngas, then CO is almost 2 times more than that of hydrogen, but in downstream applications in some cases even we need the reverse ratio, that is H2 is to CO as 2. So, some conditioning or conversion of CO to H2 is required, and that is why now in this class we will discuss how we can achieve this target, how the high temperature syngas can be used and cooled to lower temperature, heat recovery can be done, and then the acid gases can be removed to make it suitable for different downstream applications, to remove the pollutants which create problems during the processing, and to maintain the H2CO ratio. So, we have reduced syngas temperature. During cooling we need to reduce the syngas temperature and we need to extract the valuable energy from it, and chemicals are removed which can foul, corrode or erode system components, or which can poison or deactivate chemical processing agents or are environmentally unacceptable. Now, we will say how the syngas can be cooled. There are basically 2 mode of operation, one is quench mode operation and another is your boiler mode. So, one is quench mode and another is boiler mode. In both the mode the reactor part is similar, but the difference is the cooling process. So, in the quench mode the syngas which is produced here is first passed through the quench ring and it is cooled by shock. The temperature of the syngas is reduced to the temperature of saturated steam, then it goes from the side stream, and the slag or ash materials comes down. This way we can reduce the high temperature syngas to a lower value, and in this case we see 1.47 to 2.94 megapascal steam can be produced. Now, in case of boiler mode, the syngas is produced here, it is going from the side and ash is coming bottom at the bottom. So, there is no direct quenching, or it is sent to a boiler for heat recovery and exchange of heat. As a result, the syngas temperature reduces. So, this process gives us some advantage. We can get high temperature steam here with respect to the quench mode and high pressure steam here with respect to the quench mode. We see here 9.81 to 13.73 megapascal steam can be generated, and as we know, higher the pressure in the steam and higher the temperature, there is a possibility to have more efficiency in the turbine. So, that is why this mode of operation, that is boiler mode of operation, is preferred in IGCC application. Now, we will see how the particulates can be removed from the syngas. As you know, some of the reactor configurations uses very fine particles of coal, and those fine particles can be carried over if it is not completely burned, or in some applications also tar particles comes. So, those particles we need to remove. So, for the removal of those particles, there are some configuration, that is here char materials along with ash can be removed from syngas in 2-stage water wash consisting of a quench pipe, carbon separator and pack tower. Just we are spraying water and removing the particulates in the pack tower. In quench pipe, around 95% of the carbon is removed by direct water spray. So, these are two basic operations through which the particulates are removed. So, we see in this case the temperature of the syngas should be made down prior to its application. Another way of efforts are also there to use different types of oxides at high temperature to remove the gases, or we can use ceramic cross flow candle filters to remove the particulates at higher temperature. So, high temperature particulate separation, this technology is being developed and extensive research is also going on around the globe for this application. Now, by spraying water we can remove the particulates, but there are number of types of spray systems. So, this is here spray scrubber. So, in this spray scrubber, so dry gas inlet at the bottom and water injection at the top, and then there will be interaction between the droplets as well as the particulates. So, the mechanism is the inertial impaction and interception on the droplets. This is the mechanism of the separations of the particulates from the syngas in presence of droplets of the water. So, it will settle, and in this case no packed bed is used, only spray scrubber, and its efficiency say 94% for 5 micrometer particles and greater than 99% for 25 micrometer particles. And the efficiency of this system will depend on droplet size and flow velocity of the gas, and liquid is to gas ratio. These are the factors which influence the efficiency of the system. Then packed bed and plate column, another type of spray system also used. In this packed bed, one packing material is used like say racing ring, saddles, coke or broken stone. So, these are normally used for the capturing of the particulates in this. So, dry gas will come here and again from the clean gas will goes up and spray system will be there, but we have one packed bed. So, this is one type of design. Another type of design, dry gas or dirty gas from the bottom, from the top clean gas and liquid from the top, and there are number of plates. So, plates overflow, liquid will come here, again plate overflow, liquid will come here, plate overflow, liquid will come. So, that way the interactions of gas and liquid takes place, liquid droplets and particulates separates. So, this system also help to remove some gas molecules from the syngas. Now, we will see how the acid gas components can be removed. Acid gas components like say SOx, carbon dioxide, H2S etc. present in the syngas that can be removed through specific treatment steps. So, this flow sheet shows us that raw syngas which is having hydrogen, carbon monoxide, H2O, H2S, COS and stress contaminants. So, the first the COS reacts with H2O to form it H2S and CO2. So, that is hydrolysis of COS. Then H2S and CO2 acid gas components we need to remove. So, how we can remove it? Carbon dioxide removal. If we can selectively separate the carbon dioxide, then that can be enriched and it can be sequestered. So, carbon dioxide enrichment and then compression and carbon dioxide sequestration. So, one way we can get. On the other way we have H2S. So, we can remove the H2S enrichment specifically with them selectively, and then after selective separation of H2S we can use this gas for sulfur recovery and we can get sulfur, and once we can get sulfur we can produce sulfuric acid. So, after removal of sulfur or H2S we can go for further treatment of the tail gas. So, this is the flow sheet for acid gas removal, but now we will see how this can be done. So, the H2S and CO2 removal has been made by absorption and adsorption based technology. So, here this figure shows absorption based technology. From the bottom we are sending dirty syngas and from the top we are using clean solvent. So, solvent will be selective to capture say carbon dioxide or H2S or maybe able to capture both. So, then the clean syngas will go up with CO and H2, there will be no H2S, there will be no CO2 or very less amount of CO2 and H2S. So, different types of solvent has been used. This solvent which capture the acid gases either by physical or chemical absorption. So, MDA we are having here chemical absorption. What is MDA? One solvent, that is methyl diethanolamine. Selexol another solvent, that is primarily dimethyl ethers of polyethylene glycol, that is also physical absorption, and rectisol, that is nothing but the refrigerated methanol. So, that is also physical absorption. Now, in recent years some adsorption based technologies are also developed, that is warm syngas cleanup, that RTI and Eastman company they have developed this technology. They used some metal oxides, so which captures H2S. Now, we will see the comparison among these processes. So, if we see the MDA process which is a chemical absorption methods, so it removes H2S 98 to 99%, whereas CO2 is 30%. So, more selective towards H2S removal, and process parameters 30 to 35 degree centigrade and pressure is 2.94 megapascal or less. These are the technology suppliers who have developed the technologies, and here we see the cost is low, this is not this is not costly method. Then Selexol another method, H2S 99% and CO2 can be variable, and temperature is -7 to -4 degree centigrade, whereas pressure is 6.87 megapascal. These are the technology licensors, and here higher cost than MDA, but overall system cost including sulfur recovery process and tail gas treating could be more cost effective. Another is your rectisol process, H2S is 99.5 to 99.9% and CO2 is 98.5%. So, temperature minus 35 to minus 60 degree centigrade and pressure 8.04 megapascal. But this is developed by Linde AG and it is the most costly method, but high selectivity to H2S over CO2 and ability to remove COS. So, these are the characteristics of these different methods, and out of these methods Rectisol has been used widely. Now, we are coming to warm gas desulphurization. As we discussed that some metal oxides are used. So, say ZNO and H2S reacts and ZN is formed at 315 to 530 degree centigrade, and this is your adsorber, and then the adsorbents has to be regenerated. So, regenerator is also there when the ZNS reacts with oxygen and again forms ZNO at higher temperature 590 to 680 degree centigrade. So, that way it can remove the H2S from the syngas, and sulfur recovery options is also there. Sulfur can be recovered from the syngas through closed process or direct sulfur recovery process. There are two processes, and then direct sulfur recovery process SO2 plus H2 or CO that reacts 1 by N SN plus H2O or CO2 at 425 to 680 degree centigrade temperature, and sulfuric acid can also be produced from the sulfur. So, this is the closed process. So, if we have H2S plus 3 by 2 O2, then it is giving us SO2 plus H2O. This is the delage value of this reaction. Then SO2 reacts with H2S again and then gives 3 by 8 S8 plus 2 H2O, and this reactions is also possible. So, these are the reactions of the closed process through which we can get elemental sulfur. Now, we will see the different methods for the removal of acid gas components from the syngas. So, physical absorption, chemical absorptions, adsorptions and molecular sieves. Molecular sieves is also used for the shape selective or size selective separations of the molecules from the syngas. So, if sulfur in product gas is high and partial pressure of H2S or COS and CO2 is also high, then we should go for physical absorption. But if sulfur concentration is high, but this pressure is low, then we can go for chemical absorption. But for adsorption process, certainly the sulfur compound concentration must be less. So, low sulfur and then low or high pressure we can go for adsorption, and for molecular sieves high sulfur and low partial pressure of CO2, COS and H2S. Now, after the removal of the acid gas, now we will see how the CO is to H2 ratio is maintained, or how the H2 concentration in syngas can be increased. So, that is done by shift reaction, water gas shift reaction. The reaction is CO plus H2O, it gives H2 plus CO2, and this is the exothermic reaction. So, this reactions is performed in presence of catalyst, and this shift reaction can take place before the removal of acid gas from the syngas or after the removal of acid gas from the syngas. So, if this water gas shift reaction takes place before the removal of acid gas removal, then it is called sour shift water shift reactions, and if it is placed after the acid gas removal, then it is called sweet water gas shift reaction. So, we have two types of reactions, sweet shift reactions and sour shift reactions. These two reactions uses different catalyst, uses different temperature range. So, we can have two types of shift reaction also on the basis of temperature. One is high temperature shift reactions, another is low temperature shift reactions. So, high temperature means it is 320 to 450 degree centigrade, low means 200 to 250 degree centigrade. And we see the catalysts are different. Fe2O3, Cr2O3 is used for high temperature shift reactions, whereas copper, zinc oxide, aluminum oxide is used for low shift reaction. Now, instead of using separate catalyst in low temperature and high temperature shift reactions, catalysts like cobalt molybdenum alumina oxide can also be used over a wide range of temperatures. So, these are the development of the catalyst sites for shift reaction, and these are the comparison of switch shift and source shift. If we see the typical flow sheet, then it contains switch shift 2 HTS and 1 LTS, and source shift reaction contains 2 to 3 conventional stages with heat exchangers and sometimes with steam addition as required. And conversion, if we use CO conversion, how the H2 can be, how much H2 can be produced within 2 HTS steps. The sweet gas shift can reduce CO concentration from 44.6% to 2.1%, whereas source shift can produce 44.6 to 1.8% within 2 steps. So, in both the process we can reduce the concentration of CO below 1% and hydrogen concentration can be increased. Now, we see the catalyst of sweet shift reactions are more expensive than the source shift reactions, and reactor size is also smaller in case of sweet shift reactions than source shift reaction. And this table shows the typical composition of syngas before and after shift gas reactions. If we see hydrogen, carbon monoxide and CO2, this concentration changes significantly, CO2 4.36 to 35.50%, then CO 49.98 to 1.12%, and here hydrogen 43.01 to 61.53%. Now, how you will use the syngas? Once the syngas is cooled, then its acid gas are removed, then conditioning is done, then we can use it. The syngas can be used in different applications, like it can be used for hydrogen production, that we have seen. If we use rigorous shift water shift reactors, then obviously we will get more hydrogen, and all carbon monoxide can be converted to hydrogen through these reactions. Or we can use it for electricity or steam productions. The syngas can further be combusted and heat can be generated and can be used in electricity generation. It can be converted to SNG, it can be converted to FT fuels, that is naphtha, waxes, diesel, gas fuels, etc., or it can be converted to methanol. So, once methanol is derived as a chemical, basic chemicals, then from methanol we can get number of chemicals. So, as shown here. So, number of chemicals we can get from the methanol, or this syngas can be utilized in different way. Now, IGCC and polygeneration options, this option is becoming very relevant and applicable in recent years. As you see, the gasification process is costlier than the conventional combustion based process. So, we have to utilize the syngas in such a way that the economy is improved. So, the high cost of the process can be compensated by the high value of the products, end products which is produced from the syngas. That is why polygeneration, electricity, chemicals, hydrogen, etc., all productions are considered and integrated, and that is called polygeneration options. So, you see here we use coal or any carbonaceous material, then it is syngas is produced, then particulate removal, gas cleanup, then shift reaction, conditioning, then we are getting desired concentration of H2 and CO in the syngas, then we can use it for synthesis gas conversion, we can use it for FT synthesis, etc., and then carbon dioxide sequestrations we will also get, and we will be able to produce the electricity in the gas turbine and again in the steam turbine. So, electricity we can get. So, that way we can be able to improve the economy of the process. Now, we will see how different parts of the gasification system or gasification process contributes on the overall economy. So, feedstock is around 12%, feedstock handling system around 12% share on the construction cost, and gasifier, air separation unit and syngas cooling around 30%, and then gas cleanup and piping it is around say 7%, and combined cycle power block, that is turbines etcetera. So, it will be giving 33%, and then remaining components and control systems, it is around 18%. So, these are the contribution of different parts of the gasification units on the overall construction cost. So, thank you very much for your patience.